This lesson covers the topics of formal charges and resonance structures. These are two different strategies to investigate Lewis structures further in order to understand the bonding in molecules. Formal charges are the apparent charges on the atoms in a molecule, and it's a way of accounting for the electrons in a particular Lewis structure. There are cases where there are several Lewis structures possible for a particular molecule, and in those cases we use the formal charges to decide which Lewis structure is the most appropriate. The reason we know that there are different structures possible is because of our experimental studies of these particular molecules and ions. So, for example, we're going to study the molecule H2SO4. And if you were to use the strategies that you've learned so far to draw Lewis structures, this would be the Lewis structure that you would come up with. Now you'll notice in your note that the lone pairs on the oxygens are missing, so you'll need to add those in. So with H2SO4, the sulfur has a complete octet, and there's no reason for us to expand the octet or think that it needs to be. However, experimental studies of this molecule show that rather than the sulfur-oxygen bonds all being about the same length, there are actually two shorter bonds and two longer bonds between sulfur and oxygen. And that's actually indicating to us that this is a more reasonable structure by the experimental evidence. The fact that there are double bonds will lead to a shorter measured bond. So what we're going to do is use Lewis structures to explain why or justify the fact that this is in fact a more appropriate Lewis structure. It's going to have lower overall formal charges. In order to calculate formal charges, we follow this formula here. The formal charges are determined for each atom within the molecule. We take the number of electrons in the valence shell of the atom. We take the number of bonds and subtract that, added to the number of unshared electrons. Essentially what we're doing is trying to figure out if an atom in a particular molecule is following its expected bonding. So let's just talk about that for a moment on the side here. Carbon has 4 valence electrons. And from our studies of carbon in organic chemistry and in biology, we know that carbon always forms 4 bonds. So we would expect always to see carbon in a Lewis structure with a total of 4 bonds. Let's look at the formal charge on carbon with its 4 bonds. We take the number of electrons in the valence shell, which is 4. We're going to subtract the number of bonds to that atom plus the number of unshared electrons. So in carbon there are 4 bonds and there are no lone pairs. So it's following its expected bonding and there is no formal charge. Let's look at oxygen. Oxygen has 6 valence electrons. So the simplest way for oxygen to bond and to complete its octet would be to form 2 bonds. So let's look at the formal charge that results. We have 6 valence electrons and we subtract the number of bonds, which is 2, plus the number of unshared electrons, which is 4, and that's equal to 0. When we look at the sulfuric acid, we can see right away this oxygen atom is not following its routine bonding procedure. It's got 6 lone pairs of lone electrons and 1 bond. So we can expect that this oxygen will have a formal charge. Let's now examine these two molecules. We're going to find the formal charge of each of the appropriate atoms, the sulfurs and the oxygens. The sulfur in this particular Lewis structure of sulfuric acid has a formal charge that is calculated as follows. Starts with 6 valence electrons, and we subtract the number of bonds. In this case, it's got 4 bonds, plus the number of lone electrons, which is 0. So the sulfur in this particular Lewis structure has a formal charge of +2. So we can actually label it by putting +2. Now for oxygen, there are 2 different types of oxygen in this molecule. There are these 2, one at the top and the bottom, that have 1 bond and 6 lone electrons, and there are these 2 that have 2 bonds and 4 lone electrons. Let's study these ones first. We'll call them O1. Oxygen starts with 6 valence electrons. We're going to subtract the number of bonds, which is 2, plus the number of lone electrons, which is 4, and we are left with a formal charge of 0. So these 2 oxygens in this molecule have no formal charge. These oxygens we'll call O2. Their formal charge, they start with 6 valence electrons. We're going to subtract 1 bond plus 6 lone electrons, and so therefore we are left with a formal charge of -1. So the formal charge on these oxygens is -1. So when we say it's the apparent charge, it's essentially that oxygen in that particular bonding form has 1 extra electron that belongs to it on its own from what we expect. See, over here we expect oxygen to have 2 lone pairs and to share 2 sets. But instead of sharing 2 sets, it's got an extra electron that belongs to it on its own, leading to a formal charge of -1. Let's move on to this molecule here. We'll start with sulfur again. So with sulfur in this particular molecule, still starts with 6 valence electrons. We're going to subtract. In this case, it's got 6 bonds total. And again, no valence electrons. So already we can see that when we have this Lewis structure with 2 double bonds and 2 single bonds to the sulfur, which has come from an expanded octet, there's a formal charge of 0 on the sulfur. Our O1s have not changed. They're the same, so they're still going to have a formal charge of 0. And our O2s calculate the formal charge as 6 minus, and this time it's got 2 bonds and 4 lone pairs. So again, a formal charge of 0. So what we can see here is that although it seems unusual at first glance, experimentally we know that this is the proper form of the Lewis structure for sulfuric acid because of the bond lengths. And then we can justify it further with the fact that the formal charge on all of the atoms in this molecule is 0. And as we've said, the Lewis structure that has the smallest formal charges is the most stable and is the one that's favored. So let's look at an example. We've talked about BF3, and we've talked about how when we draw its Lewis structure, it can be electron deficient. And so when we draw its Lewis structure, we don't need to draw double bonds. So let's use formal charges to help us to justify that. And so that would be an electron deficient BF3. But if you're just following the steps and you looked and you said, okay, boron only has 6 after we've used all the electrons, you would expect to put a double bond to one of the fluorines. Now, when we study BF3 experimentally, we realize that this is the structure that makes sense because of the bond angles, which we'll learn about later, but also because of the bond lengths. So the bond lengths in this are all the same as one another and reflective of single bonds. If we study this molecule here, we would see that the formal charges of each of the atoms is 0. So for fluorine, starts with 7 valence electrons. We're going to subtract 1 bond and 6 lone electrons for a formal charge of 0. For boron, it starts with 3 valence electrons. We're going to subtract the 3 bonds plus no lone electrons for a formal charge of 0. In this structure, the boron starts with 3 valence electrons. We're going to subtract 4 bonds because we've added a double bond plus no lone electrons. That's going to give us a formal charge of -1. For these fluorines, they're the same as the other ones. They've got no formal charge. For the fluorine that's double bonded, we start with 7 valence electrons. We've got 2 bonds plus 4 lone electrons. So we have a formal charge of +1. So this, using formal charges, allows us to justify the fact that this is the more likely Lewis structure. Now, to note, I wouldn't expect you to draw all the possible Lewis structures for something and then use the formal charges in order to determine it, whether one Lewis structure is better than the other. What you would need to be able to do is determine the formal charges on given Lewis structures and then decide from that information which one is the most appropriate. Now next we're going to talk about bond order and resonance. Bond order is a term that we use to describe the number of electron pairs that are shared between 2 atoms. The higher the bond order, the shorter the bond, and the more energy is involved, so the harder it will be to break it. Now, it might seem unnecessary to talk about this because we already have a way to describe using things like single bonds and double bonds and triple bonds in order to describe the number of electrons that are being shared. But what you're going to find is that when we look at resonance, the bond order is not always just a whole number. You can have a bond order of 1 1/3 or 1 1/2. So that's why we need to have another term to help us to describe this. Now, we've already encountered some molecules and ions where when you're drawing the Lewis structure and you need to draw a double bond, a lot of people ask the question, does it matter where I put the double bond? So when you look at NO3, for example, as you're drawing the Lewis structure and you're about to remove one of the pairs of electrons from the oxygen to make the double bond to stabilize the octet of nitrogen, people say, do I need to choose that one, or could I choose this one, or could I choose that one? And the reality is you can actually choose all 3. And the molecule is not actually represented well with only one. It's actually best represented by showing all three possible structures. All three of them will have equal formal charges. If we determine the formal charges, then nitrogen will have a +1, and the oxygen will have a -1 when it's double bonded, and 0 when it's singly bonded. So they're all equivalent in that way. Now the reality is, rather than this double bond being in a fixed position, where the second pair of electrons is shared in between just the two atoms, the electrons is actually shared among the whole molecule. And this is why we have what we call resonance structures. The double bond is said to resonate among all three positions. And when we learn hybridization later on, you're going to see exactly how that works in terms of orbitals and bonding. At the moment, we just need to appreciate the fact that the electrons aren't actually stationary in that double bond. They're shared more freely among all of them. And we need to avoid thinking that they alternate between all three positions, but they're said to resonate. So it's more correct to think of it as being in all places at one time, but not really fixed in any one spot. Now, the reason that we know that this is happening is because when we study this molecule experimentally, or this ion experimentally, what we find is that all the bond lengths aren't different from one another. If there was just one possible Lewis structure, we would expect this bond to be shorter than the other two because it's a double bond. The reality is all three molecules exist, and all three bonds are actually the same length as one another. And not only are they the same length, but they're a little bit shorter than a single nitrogen-oxygen bond. They're said to have a bond order of 1 1/3. So each of them is sharing one pair of electrons completely. And then this double bond resonating between all three positions is sort of being shared between all three. So each one gets 1/3 of the bond order. Let's look at another example. We want to draw possible Lewis structures for ozone, O3. We want to label the formal charges and state the bond orders and comment on the bond lengths. Now, when you're being asked to draw possible Lewis structures for a molecule, it should be a clue that there's probably resonance, because I'm not going to ask you to draw more complicated ones, like the H2SO4. Okay, so when you go through the process of drawing ozone, right, you draw this Lewis structure, for example, but you made a decision here to put the double bond on this side, when in reality the other possibility is one where the double bond is on the other side. Sorry, let's take that out. So these are the possible Lewis structures. It is important to put the double arrow in between because this is the symbol that we use to represent resonance. So we say that the Lewis structures are resonating between these two. If you find the formal charges, you'll find that the oxygen in the center has a formal charge of +1, and the oxygen on the outside with the single bond is -1. Now when it asks for the bond order, because there are resonance, the bond order for each of the bonds is 1.5. They've each got a single bond, so that's 1. And then the second bond is being shared among the 2 spots. So the bond order is 1.5. And to comment on the bond lengths, we would expect the bond lengths to be the same. So these 2 bonds, we would expect them to be the same length. CH6 is a classic organic molecule. It is called benzene. And it's a great molecule to study when you are learning about resonance. We're going to look at the basics now, and when we study organic chemistry later, we'll look at it even further. Benzene is a molecule where there are alternating double and single bonds in a 6-membered ring of carbon atoms. So when we're looking at the resonance structures, the resonance structures are ones where the double bonds move position. So in this one, I started here, double, single, double, single. This time it'll be single, double, single, double, single, double. It would be impossible to have 2 double bonds next to one another, but alternating single and double bonds is what happens. Now these are the resonance structures. And so these electrons in the double bonds aren't fixed in their positions. They're actually being shared among all of the carbons. And our evidence that the resonance structures exist and that these electrons are actually what we refer to as being delocalized, so they're not localized in one position, they're delocalized or free to move, comes down to bond lengths. If you look at a single carbon-carbon bond, the bond length is 154 picometers. A picometer is times 10 to the negative 8. In a carbon-carbon double bond, the bond lengths are expected to be 133. These are the average bond lengths. In benzene, the bond lengths are 140. So they are shorter than a single bond, but a little bit longer than a double bond. And all the bond lengths are the same in benzene. So this is evidence that the structures are resonant. So that concludes our lesson on bond order and resonance and formal charges.